Hi, welcome to Vortex Algebra video number 1. In this video we're going to review symbolic versus real operators, that should be operators, and then we're going to go into a review of legacy vector algebra. Vortex Algebra was developed to provide complete and invertible real vector operators, others for vector multiply and vector divide, which we really don't have for legacy vector algebra. First, let me make a definition for what a real operator is. A real operator can be executed on a numeric processor or an arithmetic logic unit using real numbers, real numeric constructs, which can produce real numeric results. Okay, this is in contrast to imaginary constructs, such as the complex operator or symbolic operations, where we just massage symbols and equations, but there does not really have to be numbers there. Okay, neither of these two are handled by arithmetic logic. These are handled more of in an abstract manner. Now, some people might say, well, gee, I use MATLAB, which uses imaginary values. Those are handled in an abstract fashion, because there is really no imaginary operator. This is handled as if the imaginary operator really did exist. Okay, not that that's wrong or anything, that's just really what's going on, because there is no really imaginary numbers. And what we use is we use real numbers to synthesize or simulate imaginary numbers, because they're imaginary. Just like we use computers to simulate dreams, like we do for Walt Disney fantasy. These fantasies don't exist, but we use computers to simulate them. So what's symbolic versus real? Well, symbolic would be like me putting down this mathematical equation that doesn't really have to have real numbers. The beauty of a symbolic is you can manipulate entire sets of numbers and entire ranges of numbers just with a few, whereas when you put real numbers in, you're limiting yourself to one possible solution for this. Okay, so from a symbolic standpoint, you can handle multiple different solutions at once, where once you put in the real numbers, you basically have chosen one possible solution for this. Okay, so that's kind of the difference between symbolic and real. And in symbolic, you don't really ever put numbers in until actually you want to actually evaluate for one particular case. Okay, but there is a disconnect. Because for over 100 years, engineers, myself included, but I'm not 100 years old, but this has been going on for 100 years, because this is all engineers have had for the past 100 years, is standard vector, legacy vector algebra. If we ever get up, this is an imaginary made-up equation. This is just made up for this example. This isn't a real equation. And this is vector A, and the vector A and B times some arbitrary constants here. Well, what we would do in this derivation is we would just go, oh, okay, this guy can be divided out by both sides. So we do symbolic division all the time, as long as it's trivial like that. Because this is a symbolic equation, we have full knowledge that this is the exact same thing as this. And therefore, if we divide both sides by that, it should be still equal. However, there's no real operator for this. You know, there would be no way to divide. There would be no way to go divide by A in a real numeric operation, because none such exists. Not yet, anyway. So what we've been doing is we've been avoiding the issue. Me included, when we do derivations, we try to massage and do the derivation in such a way to avoid things such as this, which the only way you can go with this is numeric. There's nowhere else to go with this, because we do not really have a valid divide operator. And for the most part, we really don't have a really complete multiply operator either, and I'll show you that. Okay, but we've done symbolic manipulation in spite of the fact that there's no real operators to support the expression. So there's time to end this divergence. Vortex algebra provides real operators. Once they've been defined and worked out, they have a limited set of rules of what they can and cannot do, which is logical and not logical. Those rules are now backfilled into the symbolic operators. So the symbolic operators and the real operators are no longer divergent. Okay, but before we go in and go into Vortex algebra, it's proper to review the prior art, what came before. Okay, to understand, what it is, why Vortex algebra is superior to the ones in the past. In the remainder of this video, we're going to talk about legacy vector algebra and demonstrate its deficiencies. In the next video, we're going to discuss geometric algebra and demonstrate that its existence is based on an obvious error that somehow got past all the mathematical journals and mathematicians in the world. I don't know how. It's really bad. But anyway, so what's a vector? Let's just get a little quick review of a vector. I expect that you, before you come to this video, that you went and looked at the old Q algebra. Q algebra is the precursor to Vortex algebra. It was abandoned because there was a ambiguity, and the 17th rule of acquisition does not allow us to have ambiguities. And so I went and reformulated it to get rid of the ambiguity, and I'm much happier with Vortex algebra, which replaces it. But anyway, in that video series, that goes into review of vectors for people that may not be strong on vectors. But let me just give you a little tiny review here. A vector is basically a multidimensional line that has magnitude and direction. And what we do is we break that vector down into its dimensional components, which would be, this vector can be represented by a component along the x-axis and another component along the y-axis. And we write those two components together. These are orthogonal. They're in two orthogonal directions. These can't be added, but this is an algebraic way to write a vector. So if we're going to multiply vectors a and b, let's say there's another vector b, well, you get your two vectors, and all you do is multiply the components. You know, you do your FOIL, what they taught you in high school. And then so you have ax times bx plus ay times by times ax times by times ay times bx. And you say, what's so hard about this? Well, there's an ambiguity here. Well, let me explain. Okay, we're trying to develop a multidimensional product from a one-dimensional arithmetic. Okay, and so trying to use arithmetic multiply to synthesize a multidimensional multiply is analogous to trying to determine the shape of a three-dimensional object by the shadow cast on a wall. It requires you to infer or deduce missing information. Is this object, is it a cylinder, is it a disk, is it a sphere? You don't know. You can't tell from the two-dimensional shape, depending on how that object is turned. Because of this two-dimensional representation, you're missing critical information of the truth. And that requires you to use logic and reason to infer what's missing. But you've got to know something's missing before you can infer it. Okay, legacy algebra deduces some. The developers of legacy have deduced that the cross-dimensional products, which are these two, these are x times x is a same dimension product, y times y is a same dimension product, x times y is a cross-dimensional product. And y times x is another cross-dimensional product. And they realize that the cross-dimensional product we have to infer behaviors that a unidimensional multiply does not have. And so this sign convention was developed in order to give the rotations of the cross-dimensional products to go in the same way. It has wonderful benefits. Okay. And so the legacy algebra product in 2D, when we put in the sign convention, can be broken down into the product of a and b. This is the legacy dot product. This is the legacy cross product. So the legacy product for 2D algebra is the legacy dot product plus a legacy cross product. This produces a scalar, and this produces a vector. Now, if you want to compare the legacy products to the Vortex 2D products, the Vortex 2D products, the product of two vectors produces a matrix. A matrix that contains 8 terms as opposed to the 4 terms that we get this. So we get twice as much information. This eliminates the ambiguity we get with this legacy system. And because it's also a matrix, and this matrix can be broken down into its dot components, which are similar, and its cross product components, which are kind of similar. But again, these each have twice as much information as these. Now let's do a real example with legacy vector products. Okay, suppose we had vector A, and it's 4, 3 is the vector. We simplify, we write the vector 4, 3, and this vector would be written 7, 2. That's a shorthand notation. You had the x component and the y component. So we plug these values into that product we had shown before. Okay, and we multiply out, and we end up with 34 as a scalar and minus 13 as a vector. This is a normal vector, which has kind of always been bothersome to me. This is a two-dimensional, multiply of x times y. This normal is in the z dimension, which doesn't exist. So it's like, we're calling in dimensions that don't exist. That's been one of my problems with legacy vector algebra. And what gets worse, if you have 4 dimensions, If you have, for 3 dimensions, this normal works fine. If you have x and y, your normal is going to be z. If you have z and y, your normal is x. That's great. It worked great in 3D. 2D is questionable. But for 4D systems, well, if you have a cross product in x and y, well, then you have 2 other dimensions that could be normal to. How do you reconcile that? And so now you get ambiguity with 4D and higher with this system. And so that's the problem with legacy vector products. They're really only meaningful for either 2D, if you want to imagine an imaginary third dimension, or 3D where you actually have the third dimension. 4D, it's ambiguous. I mean, I'm sure people have tried and used it and they've come up with systems for it, but when you say that the cross product produces a normal and your cross product is an x and y, then if you've got 2 other dimensions along with x and y, z and let's say w, well, which one is the third dimension to this? And that's where one of the ambiguities are. But that's not the biggest problem I have for this. Okay, so now we have this result, which we got a scalar and a normal vector. Well, we have known properties that, thanks, the dot product can be looked upon as the magnitude of vector A times B times the cosine of the theta between vector A and B. That's this angle here. And the cross product is the magnitudes of A and B times the sine of the vector between them. So what we can do is set the values we got earlier. Okay, the scalar is equal to the cross product, the dot product, and the normal is equal to the cross product, which is the sine. And then what we can do is we can take the magnitude of vector A, because we're going to divide by vector A now, but as the ALU, the arithmetic logic unit, we can't have knowledge. Okay, in an arithmetic logic unit, it only has the numbers. It doesn't have knowledge of what went into the original product that we're trying to divide. So we're going to divide the product AB divided by A. Symbolically, we know the answer should be B. But for an ALU, the ALU does not have that information. All he has is this 34 minus 13n, and he's got this other vector, 4, 3. He's got to divide this into this. Okay, so first thing we're going to do is we're going to take these 2 quantities and divide them by the magnitude of vector A, which is 5. So we divide this by 5 and divide this by 5, and then we end up with 6.8. Now R here is going to be the magnitude of the resultant vector. Okay, got rid of the A and B because we don't really know if the value is going to be the A or B of the original vector. So we've got, this is whatever our result is. And the cosine is going to be the theta is going to be the angle between the original vectors. So then what we can do is we can divide these 2 guys out, which comes out to be tangent, solve for the tangent, and then we get the angle. So this angle we can determine is like minus 21 degrees. Okay, and then what we can do is now we can put this 20 degrees back in, and then we can solve for the magnitude. So now it looks like we have the full answer. We know that the magnitude of the resultant vector should be 7.28, and the angle, what does this angle mean? What does it mean? Well, ostensibly, we either have to add or subtract this angle to our dividend to get the right, but do we add it or subtract it? There's where the ambiguity is. We don't know what to do with this. Okay? I mean, let's go through again and divide by the other vector. Okay, this time we're going to divide by vector B. Okay, this time we end up with the right magnitude and the right angle, but again, it's the same angle. But what do we do with it? We don't know. There is not enough information that says we either need to add to or subtract this angle from the angle of our dividend or divisor. There's where the flaw is. There is not enough information to complete this. We get close. We get almost all the information available. We just don't know what to do with this angle. And then what happens if we divide by... Dude, will you please stop it? Okay. So we're dividing by A. We know when we're dividing by A, because we have foreknowledge, that the angle must be added in order to get to the other angle. But what if you're dividing by vector B? Vector B means you're going to have to put the angle the other way. You have to negate the angle. Okay? Now, I know that might be kind of confusing. I've gone over this real quick, but for those people that are interested, you can follow this. It's very simple. And ultimately, the amplitude we can get, that's not a problem. That's a no-brainer. and we get the same magnitude, the same angle, regardless of which way we divide. If we get the same angle regardless of which way we divide, then we have no understanding of whether we add or subtract it. In one case, we have to add it. In the other case, we have to subtract it to get to the right answer. And you can do that on your own and see that that is, in fact, the case. Okay, the only way to know whether we have to add or subtract that angle is to be able to carry along enough information to know which of the original products a divisor was. However, this would only help for trivial divides. Because what if we had AB over C? Well, we wouldn't know because C is not part of the original products. So whether we add it or subtract it to it, it's completely ambiguous. It's one or the other. It can't be both. So we have two possible solutions, and there's an ambiguity. And the 17th rule of acquisition says ambiguity in a modular theory, in this case in math, indicates that a modular theory is a special case of a more fundamental explanation. In other words, when you have a special case of a more fundamental explanation, that's the same thing as the shadow. The shadow is a subset or a special case of whatever the object was that cast the shadow. And because it's a special case, you've lost information. And the reason that you get the ambiguity is because you lost information. Okay, and so rule of acquisition 17 is one of the most profound rules of acquisition. It really helps propel us along probably more than any other rule of acquisition. So the conclusion is the legacy product is missing information which prevents the synthesis of a real vector divide operator, even in the case of trivial divides. And engineers have been performing symbolic division, but can only do it for trivial cases. Again, there is no valid solution to the non-trivial case of AB over C. This has not changed in over a century, and in the next video we're going to discuss geometric algebra, which claims to have a solution for this. And I'm going to show you that geometric algebra is really mistaken. I want to take a shout out to my Patreon subscribers for being patient, and I want to thank them for their support. We're basically going to put vector Vortex Algebra out incomplete because it's as complete as I need it to be to go forward. And in the paper, the areas that are marked complete are said these are incomplete. They're minor things. They're not going to slow us down, and they're those things that we'll come back to if we determine we need them later. Or somebody else may be able to figure them out and save us the trouble of having to do that. That's fine too. Anyway, thank you very much. No more voodoo physics or math. Oh, I meant it to be the new one. The new one didn't come up. No more voodoo physics or imaginary math.